Hello, good morning, guys. So today we're going to review how to do these questions from Chem2OA3, which is Organic Chemistry, Introductory Organic Chemistry 1 at McMaster. So in this first question, they're asking us to draw in all of the lone pairs around all of the heteroatoms in this molecule. So basically, we're first going to start with this question over here, where for this question, let's start with the oxygen over here, right? So we draw the lone pairs according to whether the octet is full or not, right? So over here we see that the oxygen has three bonds, which means the octet is not full because 3 multiplied by 2, that means it only has 6 electrons in sharing with it, but it actually needs a total of 8 electrons to be shared with it. Um, so basically, it needs two more, and since it's not charged, so we can say that it has a full octet, and we can draw like two lone pairs over here, right? And once this happens, we can also say that overall, if you look at the number of bonds and the number of lone pairs that we have, the charge would be 6 minus 3, which is the number of bonds, minus the number of lone pairs, right? So it should be a positive formal charge over here for this one. Then coming on to this nitrogen, nitrogen is actually pretty much fine with like three bonds. And so basically, to fulfill its octet, we would have this. We would fill in two more lone pairs again. So we always do the formal charge after filling in the octet, right? That is our number one rule. So always fill in the octet and add in the lone pairs and then do the formal charge, okay? And now the formal charge calculation is 5 minus 3 bonds minus two electrons in lone pairs, right? So that will be a zero formal charge. Coming on to this nitrogen, that will be also quite similar. It has three bonds, and to fulfill its octet, we would have two lone pairs over here. And for this one, if you look at this one, so this already has like two bonds from here, and one here. So in total, that's four bonds. Four into two, that gives it eight electrons. So its octet is already full, right? So instead of trying to fulfill its octet, now we are just going to try and determine the formal charge on this atom, right? So 5, which is the number 5, which is like the number of valence electrons that nitrogen usually has, minus the number of bonds. It has four bonds, two here, one here, and another one here, but it doesn't have any other lone pairs, right? As we initially said, because it already has a full octet, so we didn't add in any lone pairs. So basically, 5 minus 4, that's a positive formal charge for this nitrogen over here. And coming on to this oxygen, so this has two bonds and it doesn't have a full octet. So basically, that means the two bonds are giving it four electrons. It needs four more, so we're going to add that to fulfill its octet. And after this, we can see, you will remember, because we will be doing lots of questions like these, that oxygen usually does not have any charges when it has two bonds, but when it has three bonds, like over here, it usually does have like a formal positive charge. But on here, it is neutral. And you can also calculate it by looking at how, like, 6, that is its number of valence electrons, minus 2, which is the number of bonds, minus the number of electrons in the lone pair. So 6 minus 2 is 4, minus 4, which is the number of electrons in the lone pair. And for chlorine over here, if we look here, it has only 2 electrons, right? So basically, to fulfill its octet, it needs 6 other uh, lone pair of electrons, 6 another electrons in its lone pair, and it won't have any formal charge. And now, if we look at the boron over here, the boron is an exception. The boron is an exception. Sorry, just let me erase this. Uh, Yes, so the boron is an exception. So boron is actually fine with three bonds. You have to remember, right? What is fine with three bonds? And there are like three elements that everybody should remember, which is that beryllium, boron, and aluminum, right? So beryllium is fine with two bonds. It doesn't need to have a complete octet. And similarly, boron and aluminum, they are also fine with three bonds and they don't need a complete octet, right? So over here, if we look, the boron has four bonds, right? Since it has four bonds, it has one extra bond, right? So basically, the number of lone pairs for this, the number of valence electrons for this is three, right? That's why it's fine with making only three bonds. It doesn't need more than that, right? So when we do 3 minus 4, that gives us a negative charge, negative formal charge. And for this nitrogen over here, if we look, nitrogen always is fine with um, five valence electrons. But first, let's take a look that it needs to have a complete octet, right? So over here, we complete the octet, and then for the formal charge, 5 minus 3 minus 2, that gives it a neutral formal charge. And then, if we are to determine the molecular geometry and hybridization around the indicated atoms for number one for boron, right? So, the boron over here, we can see that it has three bonds, right? So, boron will be sp3, right? So, and anything that is four, number of so basically this is the steric number, right? This is the steric number. I will just abbreviate it as SN, right? It is calculated by doing number of sigma bonds plus number of lone pairs, right? So boron over here doesn't have any lone pairs. It only has four sigma bonds. Four sigma bonds is equivalent to sp3 as your hybridization, right? And sp3 is always tetrahedral, right? That's tetrahedral. It's your tetrahedral geometry. And now coming on to this carbon over here. So we know that this is involved in a triple bond. So we automatically know that that should be in SSSP hybridization. Why? We can also confirm it using the number of bonds it has. So it has one sigma bond on this side and one sigma bond on this side and one sigma bond on this side, right? The other two bonds, the from the triple bond, they're all pi bonds, right? So we're not going to count them. So in total, it's two. That's why it's sp, right? That means, and sp means linear, right? So we have to keep that in mind that it's linear. Okay, so this is SP linear, and you just do that using the steric number, which is 2 over here. And now coming on to number 3 over here, which is our nitrogen over here. So over here, we can see that the number of sigma bonds is 3, and the number of um, and this pi bond actually we're not going to count, and this lone pair actually we can see that it's allylic to this pi bond, right? So because it is allylic, that means it's actually a delocalized pair of electrons. So that's why we're not going to include it in our hybridization, because it's going to interact or be a part of the resonance system in this six in this ring over here. And that is why we're only going to count it as an sp2 hybridized nitrogen atom, because the steric number over here is only 3 and not 4, because of this lone pair, right? So over here we count lone pairs as 1 only, right? We don't count them as 2. Over here for steric numbers, we only count the number of lone pairs as 1. Each lone pair counts as 1, but it's different for formal charges where you count each electron of the lone pair as an individual thing, right? But over here, for steric number, for hybridization, you count the lone pair as 1 only, right? And then you also have to take care about whether it is delocalized or not. One of the major things which happens when it's delocalized is when it's allylic. What do I mean by allylic is that it is next to an atom which is involved in a pi bond, right? So this nitrogen over here is adjacent to a carbon which is involved in a pi bond, right? And over here you can see that there's also like hyperconjugation happening over here, right? So you can actually move these pi bonds, like this pi bond over here, this one over here, this one over here, right? And you can basically do conjugation of it. This is going to be like an elongated conjugated system, right? But nevertheless, right now over here this lone pair is on an atom which is adjacent to an atom involved in pi bonds, right? So this means that this is not actually an sp2 hybridized. It is actually in a p orbital, in a separate p orbital, and therefore participating in resonance.